Okay, well, I'm gonna go ahead and start here, even though it's just us at the moment. Hopefully we'll get some more people show up here for class. Yeah, I switched over to we'll just record these for the time being, since I'm having so much problems with it. So yeah, let me know. I was gonna remind people about the thing I asked for at the end of the week. So. If we have any questions about getting that accepted and what you need to do for that. So I didn't get a chance to check yet this morning. So yeah, for the people that are watching this after the fact, I'll try and check those today, see what things people are selecting. So I know I saw a couple people had accepted it yesterday, or yeah, the day before after class. So, but I'll try and make at least a first check on that. See if anybody has the same data set that they're asking to use and that kind of stuff. So, but yeah, just as a reminder, make certain you get that done. By Friday here. So. And don't forget, so we're working on assignment 3. So yeah, my plan for today, I was going to finish up talking about the introduction to the linear regression, and then we'll get into some of the stuff that's kind of directly that's asked to be done on the assignment 3. So probably by the end of the class here, I want to jump up and look at the actual assignment question things, but. So let's just go ahead and go back to kind of where we were at the other day. So if you read through the first notebook for this unit here, we've gotten up to hopefully, kind of a motivation for kind of the heart of linear regression. Okay, so if you understand what we're doing in terms of, we've got a set of data points. In this case, we are making an assumption. So linear regression is making an assumption that there is a linear relationship between one or more independent variables that we can use to model or predict the dependent variable. So the simplest case is when we just have one independent variable, which is what we're looking at the moment, but that easily extends to as many input features as you want to fit, try to fit a linear relationship to. The only difference is if you have 2 or more features, then you're actually fitting like a plane or a hyperplane, but it's still a linear type of model. So later on in this class, we'll talk about fitting a nonlinear function, a nonlinear model to a set of data. So not all data has a linear relationship where for 1 unit of change on the size of the square feet of the house, we're assuming that there's a constant unit of change in the price. That's kind of what it means to be like a linear model here. So yeah, and that's really what the slope is that we had last time. So the slope that we came up with as the best fit. We didn't really say how we figured out the best fit, but last time we had said that we'd shown using the polyfit function in order to get the line, or at least to get the slope and the intercept that we were using here. So this is really saying basically the slope that for every since it's the ratio of y to x, so for every 1 square foot we get 0.13 thousandths of a dollar, so $130 change in price, something like that. So if I'm doing my math right in the head. So. Morning. So the only thing that's missing, is kind of the important part, is so how there's an infinite number of lines that you can fit to a set of data. So how do we pick the one that is the best fit, that's the best linear model in this case? And that's the purpose of the cost function. And you know, if you read this or if you're following along on our last meeting on Tuesday, you maybe have a bit of an intuitive feel of how that goes. So what we want to do is we want to figure out the error. So for if you have some hypothesis, so some model line, so when we have just a single feature, that means that we just have our hypothesis is a set of what we'll call the theta parameters, the slope and the intercept. So we've got two parameters, right? So we could have an infinite number of those, but just consider that we have one slope and one intercept. That would define a line against our set of data, right? So we had, like this plot here, you know, we could have had other lines than these two, right? But consider this line, or maybe some other line that we would draw. So how would we figure how good of a fit that line was? Right? So, you know, the first idea is we're going to define this idea of the error. In fact, we're going to be using the mean squared error usually to measure the performance of a regression problem. So when we're fitting a line or fitting a set of data to some real valued numbers. Right? So the error is really just the difference between the actual value, the regression label, and the predicted label. Right? So here, above here, the y-hats, we had figured out the predictions here. So, you know, the predictions, if you use predictions from scikit-learn, it's really just doing this. It's just, so once you have the theta parameters, the intercept and the slope, to get a prediction for some particular input, so the size in square feet, you just multiply times the slope, add the intercept, that's going to be your prediction. Right. So, you know, and that directly corresponds to, like, these are the predictions, the orange X's here, right? So for each, we're just making predictions on the data that we fit the model with in the example at this point. So for example, this one here, for a little bit over 1,000 square feet, the prediction would have been on the line right here, the actual value is at. So the error is really the difference between the prediction and the actual value at each point. Right? So sometimes, you know, we can be really close, you know, almost zero error. Sometimes we can be really far away, right? So some of these have large errors here. But that's all that we mean by the error here. So for this particular one, the very first one in our set of data, we had an error of $45,000 here.
There's also a difference between the error and probably the standard deviation or area?
Well, I mean, those are all measures that we can have. So, in fact, we will use the average of this. So, you know, this is just an error. So I don't know if it's exactly answering what you're asking about, but this is just the error for one point. And kind of the point, me scrolling back and forth between these two, is that, you know, I mean, it can be really, for some given point, the error can be really small or even zero, but it can also be large. So the important thing for if we want to figure out the performance of this line or some other line for this set of data is, on average, how it does. And you know, you could also calculate the standard deviation to be useful information. So whether we have a large number of points that are far away from the average, or they're all really pretty close to the same error that are a difference from there. But yeah, we're just going to use the mean usually. Although the first thing, before I jump to that and jump ahead a little bit, so sometimes we overpredict and sometimes we underpredict. So like in this case, so if we're just taking the difference between the actual and the predicted, oh no, the other way around. So if we take the difference between the predicted, we're using like a hat. We're using that same notation that we did before. So y hats are our predictions, y is the true value, the actual regression label. So if you subtract it that way, we were underpredicting. So we have a negative error here. So if you just summed up those errors, you know, since sometimes you overpredict and sometimes you underpredict, you would get an error close to zero, or you might get an error close to zero. Right? right? Depending if the over and the under predictions kind of equal out or not. I mean, you wouldn't always get an error. You wouldn't always get a zero. So if I have a line like this, everything is everything's over predicted. Everything's above the actual prices. So all the predictions would be negative, and you get a really big negative value, right? But something that's actually a good model is going to have close to zero, because all the you're going to get equally things above and below, so they're probably zero out. So anyway, because of that, using Python, we can in just one vectorized step get all of the errors, right? So because we've already got all of our predictions in one array, so there's just a vector of, we had like 47 house prices in this one, and that was our true house price, so we can get our errors for all of them in just one step by doing a vectorized subtraction. So that's all of our errors. If we sum that up, we were using the actual best fit line. So the best fit line has a property that the sum of these errors is going to be zero, because it's going to be a line where all of the things above and below cancel each other out. Right? So you'll see that property here. But if we did this for a different line, you might not quite get a zero error. In fact, if you have a really bad fit, you get something that's far away from zero. The sum of these is not really a good indication of how well it's doing. What we really want to know is the sum of the magnitude of the errors. So sometimes we underpredict, sometimes we overpredict. A better, a first intuition, a first thing most people would try if they follow this line of logic is, well, let's just take the absolute value. So that's a better indication. So in this case, if we take the absolute value, this is saying that the sum of all of the errors that we had, the magnitude, we're ignoring whether we under or over predict. We were just sum 2044. But what we might really want to know is kind of what on average, what our error is on average, whether it's under predicting or over predicting. Right? And that leads to the idea of the mean absolute error. So if we just take the mean, the average of that, so divide by the number of samples, which n is the number of samples here. This is kind of meaningful. So this means that our error on average is about $52,000 for this model. Okay. But we could use that. We could compare that to other lines, and we want to get that as small as possible. The smaller, the better. In actuality, instead of taking the absolute value, we usually take the square of the errors. Okay, so that's what the ordinary least squared in the stats model refers to. So why we do this, if you read this notebook, the reason why we do this is there's a couple of reasons, but this is more tractable mathematically than the absolute value. So, for example, you can get an exact equation. That's really what the normal equation is. You can, if you use the square, you can fit an equation that you can minimize and find out exactly what the in this case, the theta parameters, the slope and the intercept need to be in order to get the smallest possible mean squared error. Okay? We'll come back to that. So, but the mean squared error, which is what we'll usually use for measuring the performance of linear regression, it does exactly what we just did before. So this is notation for the stuff we just did by hand. The only difference is instead of doing the absolute value, we take the error. So this is the notation for the error again, right? So we take our inputs and we multiply by the theta parameters using linear algebra. So the result of that is our prediction. So this is really the y hat right there. And that's the true values, the true regression labels. So the difference between those two errors and then instead of taking the absolute value, we square them, right? So, if you take the square of something, it'll be positive, right? So the squares will be, if the error was 0, it'll be close to 0, but the larger the magnitude of the error is, the bigger the square will be. But it'll be a positive number, right? So then, we sum up the squares of the errors and take the average of that. So that's what the mean squared error means here. Okay? So this is relatively easy to calculate by hand, but you can always get that error from like scikit-learn or stats model. So you did that on the second assignment. That was one of the things that we were asked to get, like the score of how the model was performing, basically. So yeah, if you read this notebook, we kind of walk through calculating that by hand, but it's relatively easy, especially using Python and using the ability to do vectorized calculations. So again, kind of one of the reasons why we set it up the way we do is it makes it so that we can very simply specify in the code or do it in the mathematics in an exact way for like the normal equation. So in Python, though, our error we showed before, so the error is really just the difference between the predictions and the true values. If we want to calculate the mean squared error, take the error squared, divide by the number of values, and that will give us our mean squared error. Although, this is the average of the squares, so we can also, so often people want to know what the root mean squared error is, because if you take the square root of that, you get back to the same units that you had before, right? So this is, again, we can think of that the root mean squared error is telling us that we approximately have, when we square the errors, instead of taking the absolute value of the errors, we're getting approximately an average of $64,000 off in this case, right? You can't really compare the root mean squared error to the mean absolute error. It's kind of like apples to oranges, but if you're comparing two mean squared errors to two root mean squared errors, the lower one is being better at predicting. So the closer you are to 0, the better your line, your model is that fits the data. And the larger further away is, the worse it is. Okay. So yeah, you can do that all in kind of like 1 or 2 lines. So that was kind of a summary of it again. So again, though, this is we're not yet saying. So how do you find the best data? So we've made it precise. We've made the question precise. So what it becomes now, if we have a measure, and if you believe that this measure, the lower, the closer it is to 0, the better the fit is, the better the model is. So then the question becomes, how do we find the parameters, the slope and the intercept, if we only have one input feature, that will get the smallest possible mean squared error or root mean squared error? Okay. And I'm going to skip over the normal equation today. I mean, sometime maybe I might come back to it, but one advantage of using the square is this isn't too tough to understand, but you can actually specifies an exact equation, and if you solve this, you will get the parameters that will give you the lowest possible cost function, the lowest possible mean squared error by putting these in here. So we'll kind of come back to this as well. So if you know a little bit of calculus, this relies on basically taking the function and finding the minimum. So this comes from taking the derivative of the equation that we had before, setting that to 0, because the derivative when it's 0 will be the place where it's the minimum or the maximum of the function, but it'll be the minimum in this case. And then solving for that will give you the theta parameters, the slope and the intercept, that give you the minimum here. So, but we'll come back. So if you look at the next notebook, let's jump to that. So if you look at another method for finding that is gradient descent. So if you understand gradient descent, that helps understand what the normal equation is doing as well. Let me go ahead and open up the, oh, not that one. 5.2. Let me see if this reruns here. Just want to check my performance real quick. Still doing okay. All right. Oh, that didn't run. What happened? Oh, yeah, I forgot this. If you are using the development environment for our class here, so one of the cells in this notebook tries to make a movie of stuff. So you probably have to install FFmpeg. Probably don't do that because it's relatively big, but I'll just show real quickly. If you're interested in actually getting the movie to compile in your development environment, you should be able to do like a apt install FFmpeg library to get that in there. You have to do that as root, so you have to do an sudo. Nope. Oh, you might have to do like an apt update, so probably will if you never did an apt update before. You first have to update the list of packages that you have inside of your Linux, Debian Linux that's running in the container, and then the install should work of the FFmpeg, I hope. This might be relatively big, but I don't think this will take too much time here. But yeah, I'll let that run. So once we come back, once we have that back, it should be able to run that, hopefully. So that's just using that external library to make this movie here that's needed in the middle of this notebook here. So, all right, so the mean squared error cost function, can be solved exactly, so that's what the normal equation is. Another way to find the minimum, so to find the slope and the intercept parameters that would give you the smallest value, is by a method known as gradient descent. Okay, so this is an optimization method. There's many kinds of optimization methods. This is one of the basic ones. So this is a good thing to understand in general, kind of how this works. So given our function, the idea is that, so given that function, we want to find the set of theta parameters that minimizes the cost function. That's what the name cost function means in this context. That's what we usually call it when we're turning something into an optimization problem. So once we have the formal definition of our cost, we can try lots of different solutions. So the easiest thing you can imagine is a random search. So I could just try different slopes and intercepts. Those would define all kinds of different random lines. Just always remember the one that gives me the lowest cost, right? So basically a random search. That's one way you could try to optimize. Not a good way. You might not ever find a good solution doing that, but you could do that. So, so one thing to understand: the reason why the gradient descent works for the mean squared error is it has a particular shape of the function. Okay. So, and this stuff's kind of coming directly from Dr. Ng's notebook. So he has some lecture videos about giving an intuition for how the cost function works and how gradient descent works. Like the simplest idea, let's say that, remember how we're doing this here. So let's say we have a line, points on a particular line. So, and we're going to ignore the intercept. The intercept is going to be 0 here. So the slope of the data that we're trying to fit a model to have just a slope of 1 and an intercept of 0 in this case. Right? And since the intercept is 0, we're going to kind of ignore that. So we can just try things with different slopes to see how that affects the cost on this example here. Right? So, so the actual data, since the intercept is 0, the slope is 1. So for each x, the y is the same, right? So the point 0, 0, 1, 1, 2, 2, 3, 3 are on the actual line that we're trying to fit. And I guess I should maybe be a little precise here. The thing, the real thing that we're trying to fit is this model here, where that has a slope of 1. Okay? And there's no noise in the data here. Right? So we can actually, if we have a line, if our model actually has a slope of 1, we'll end up having an error of 0. But if we have other lines with slopes of non-1, we'll have non-zero errors. Okay, so let's just, so we define our cost function for the mean square error here in this example. This one takes a NumPy array of values to compute the mean squared error of, and as well as the true labels for those values. Okay? So basically, the x, the theta is actually the hypothesis of the line we're trying to calculate here. So in this case, we're always using an intercept of 0, so this just has one value right now. Theta 1, which is going to be the slope. So anyway, given the slope, we can get our predictions by multiplying that slope times the inputs for our predictions, and then we can calculate the mean squared error like we just did a few minutes ago in the previous notebook here, right? So taking the square of the errors, summing those up, and then dividing by the number of values in that we're making predictions on to get the mean of those. So, right, if you didn't quite follow that or read through the notebook, for example, so it's relatively simple. So if the slope is 1, that represents a model that exactly goes through all the points that we're trying to fit. Okay, so you end up with an error of 0. But if you have a slope that's non-1, that's like a little bit too big, 1.1, or too small, 0.5, it won't go through all the points. So there'll be some error at that point. So you get so the further away from 1 r, the bigger your error will be. All right. And this function is vectorized, so for a reason. So instead of testing one theta parameter at a time, we can actually pass in an array of theta parameters. So, so if we try all the theta parameters from -1 to 3, and pass that into this cost function like we have it defined there, these are the errors, right? So the slope of 1 has an error of 0, and the non-1 slopes have larger errors the further you get away from the slope of 1, which is the true slope of this function that we're trying to fit. Okay? So the reason we do that is so that we can see what the effect is of the changing theta as a function of, so as theta changes, how does that affect our cost function? Right? So for the one that we just did, we tried different values from -1 to 3. And it looks like this. So it's 0 at the true slope, and the further away that you get, since it's the square of the errors, the larger the cost is. Right? And since this is a quadratic function, this is really a parabola. Okay, so because we're squaring the result, so it's really a smooth function. So if you increase your step size, so we have 101 points. So this is increasing what's known as the mesh of the function we're trying to do here. So we only had like 6 points before, but we have 101 points from -1 to 3. You can begin to see that it's really a quadratic function here. It's a parabola that has a minimum at 1. A minimum, and the slope is exactly the slope of the points we're trying to fit. And the further you get away from it, the worse the cost is, the higher the cost becomes. So yeah, I mean, there's a couple of points on that, but this is kind of important. So this is also an answer to why, the normal equation works, the exact method, because by taking the square for our cost functions, we're defining a function of our input parameters that's going to be a parabola. So the square is going to look like this. So if we have more than one function, it's going to be 2, 3 higher dimensional. So, but it'll always be bowl shaped. It'll always be concave with exactly one minimum. All right. And if you know how derivatives work, if we can calculate the derivative, which is the slope at different points, you know that the minimum of a quadratic, of a two-dimensional function like this, happens when the slope is 0 down here, or that could be a maximum potentially if a parabola looks like that. Right? If you if you took a calculus course, you kind of remember back to doing stuff like this with derivatives, finding the minimum or maximum of functions here. So that's really what the normal equation is doing, and that's really what we do with gradient descent as well, but instead of doing it in a exact method, I'm skipping ahead here a little bit, but as long as we have a function that we can find the derivative of, we can pick a point at random, like say a slope of -0.5. We can find the derivative of our cost function at that place, and so in this case, the derivative is going to give us a slope that's negative here, since it's in this direction. So if the slope is negative, then that means that we need to try a value on this feature in that direction in order to go down to get smaller costs. So that's really what the heart of what gradient descent is doing. So another reason why we use the square is because it is it's well behaved. We take the derivative of a quadratic as a cost function, right? So it's defined. It doesn't have any discontinuities. So that means that for gradient descent, we can find the derivative with respect to, this works even if you have more than one feature like we have here. So if you have the slope and the intercept, or if you have more than one input feature, you can find the derivative with respect to each one of those, and that will tell you, at least along that dimension, whether you need to make that bigger or smaller to go towards the global minimum, the place where the cost is the smallest for the function that you're trying to fit, right? Okay, so and I don't know if that so that it'll always be a parabola. In this case, it's that particular parabola because we're trying to fit data that are these data points. So these data points basically have a slope of 1. But if we have some other data with a different slope, you will still get a parabola that's concave with a minimum, just minimized at that particular slope. Or if you have more than one feature, it will be in multiple dimensions, but it'll be bowl shaped. There'll be one global minimum for the function. The other thing about this is that for real data, there's going to be some noise in there, so you won't always be able to. The minimum won't always be at an error of 0. So if we'd had these points, but they were a bit noisy, so they weren't. The data we were trying to fit maybe had some random noise in it. But the real data actually was a slope of 1. It's just that when we measured it, there was some noise in the measurements, or there's other sources of error that can get this away from kind of the value of the true model that's producing that data. But yeah, so with data like this, you wouldn't get a slope of 0, but there would still be a minimum, just some minimum where the error or the cost is above 0. Or something like that. But there's going to be one place. Right? So even with some noisy data like that, conceptually, underneath, because it's a quadratic, because it's the cost function is a square, it will be forming something like that with one global minimum that we can search for. So we go. So the rest of the notebook here is just further and further adding in more details or more complications to that basic idea. So the first thing we might want to do is see how that looks if we have actual 2 dimensions. So we use a set of theta parameters that is both the slope and has both the slope and the intercept in there, right? So theta 0 and theta 1. So theta 0 is going to be our intercept value, theta 1 is going to be our slope value. We're still only using one feature, but we're not keeping the intercept clipped to 0 here. We're going to allow it that we have 2 parameters. So yeah, in this case, we're using an intercept of 1 and a slope of 1. Right? So when we so I'll just explain this here. Right? So now, since we have 2 parameters, the cost function we can't visualize it on a graph like we did before. We need a 3rd dimension. Right, so we've got both theta 0 and theta 1, which can range, but we're fitting a line now that has a slope of 1 and an intercept of 1. Right? So that means that the minimum, the cost will be 0 when theta 0 is 1 and theta 1 is 1. Okay? So all we're doing here is we're using what's known as a contour plot in order to visualize how the cost changes as both theta 0 and theta 1 are changing. Right? So we use color to indicate the 3rd dimension in a contour plot like this. Right? So basically this is 0 right here, where you get a 0 cost, and the slope is 1 and intercept is 1. And the further away you get from that either way. So even if you hold the intercept 1 constant, so it's a little bit, so in that direction, it doesn't vary very fast, so maybe we'll go the other way. So even if you hold the slope constant at 0, if you change your intercept to 2, it begins to rapidly get worse on your cost. Or if you change your intercept to less than 1, down to 0, the cost begins to get bigger and bigger. Right? So yeah, sometimes this is one of the difficulties of gradient descent. I won't be able to get into a lot of details on it today, but so gradient descent, because the cost function is a parabola, it will eventually get down to or get close to the minimum. Okay, so what we're doing for gradient descent is we start at some random location. We figure out the gradient for that, and that tells us which direction to go. But the direction that we go, we're going to take some step size. So we might go 1 unit in the correct direction. That might lead us here. The problem is that you can end up with, well, one problem is you can have functions where it's kind of really flat, close to your minimum. So you get here, and then it will take a really long time to actually get to the global minimum. right? So the rate of, that's known as the rate of convergence. It might take a really, really long time in certain places of your cost function that you're iterating through here and taking step, if your step size is too small, before you get to the actual global minimum. Okay. The other problem, though, is you can have functions that vary real fast. So if your step size is too big in that case, so if I need to go this direction, I might go too far. In that case, you can actually start diverging. So if I take a step and I'm over here, I've actually gone to a place that's a worse cost than a better cost. So then I take another big step, and I might go here, and then you start going further and further away from the solution. So instead of converging, if your step size is too big for a gradient descent, you can diverge, go away from the minimum. Okay. So both of those are problems. So gradient descent, unlike the normal equation, is not an exact method. It's an approximation. So we start with just a random guess. We use the gradients to figure out which way, how we need to change our parameters to move towards the, a better place, to a place with a lower cost. We take a step towards that cost. We keep doing that until either we're satisfied that we're as close as we're going to get, or we detect that we're diverging, or there's some other problem. Right? Or maybe we just do that for 1,000, some fixed number of steps or something like that. So yeah, sometimes it can be tough to see the shape of your function. So like here, we're doing the same contour plot, but we plot the logarithm, right? So by taking the log of the cost function, we can a little bit better see the contours. And yeah, we're using lines now instead of for the different contour levels here. So let me see if my FFmpeg is installed here, so that should run, I hope. Yeah, there we go. This is meant, again, to try and show you, to give you an intuition for what what gradient descent does. So this is the most basic kind of optimization method you can use, but if you understand how gradient descent works, most all the other ideas of optimization methods that are most sophisticated still are going to be kind of based on the same idea, right? So it's good to understand this one because you can understand most of what it means to do like an optimization problem. So in this case, if we start with a random location, so we're going to start with a slope of 1,800, and I might have that reversed. I can't remember. So like an intercept of 1,800 and a slope of I think that's actually the slope on these diagrams here. Look at this. So this is the cost function here, and this is the just the plot of our data that we were using before, and the actual price of those data points. And so if our first guess is over here with a slope of -0.1 and an intercept of whatever that is, 1,700 or so. If we look at it, here, if we calculate the gradient here, we will know that we need to make the intercept smaller. We need to go that direction on the intercept, and we need to make the slope bigger, right? So this needs to increase, but that needs to decrease. If we take the derivative with respect to these two parameters here. So we might take a step along that. So that point here represents that line with an intercept of 1,800 and a negative slope. So if we take a step according to the gradients, we might next go to that point, right? And we still need to go both directions there, but that represents that line. So each one of these lines, we're taking a step based on calculating the derivatives in order to follow the gradient towards the smaller cost. Here the cost isn't going to be zero, so I should have put like a color bar on here. So, but yeah. So now since our data has some noise in it, we can't get a line that will get a zero cost, but we will be able to get down closer and closer here until we get to that here, which is that should have that same intercept of about 100 or something and a slope of about 0.14, right? So this is the same data that we already fit with like polyfit, so we kind of know what the best line is according to the cost function, the root mean squared error is. Okay, anyway, so yeah, so I hope, people can get to a point where they can understand this. So this is a good visualization, a good intuition for building intuition of kind of what's happening here. Right? So we're still only using two parameters, the intercept and the slope, but the heart of the gradient descent works that way. So as long as we can find the derivative, we can just start at some random place and then use that to take small steps, which basically are changing the parameters with respect to the gradient, so that we move in small steps towards smaller and smaller version of the cost, right? So again, if the step isn't too big, we shouldn't diverge. And if our step isn't too small, so if we take really small steps, it could take a long time to get there. So you have to do other stuff in order to be efficient with using gradient descent to get to the to get close to the minimum in a reasonable amount of time. We won't talk about those today anyway. So there is a lot more details if these all run. I'm going to move on from this. I might come back and talk a little bit about, so later on, it'll be useful to understand some of these things that are discussed here. But yeah, if you follow that, you kind of have the tools, and that's to implement gradient descent. And we actually show an implementation of gradient descent by hand in the notebook here. Yeah, starting here. I will just mention quickly, it'll be good to look through this code so we can figure it out. It turns out that, calculating the gradients using the mean squared error function, the formalism might look kind of complicated, but it comes down to something really easy. So this function here is actually calculating the gradients, calculating the derivatives with respect to each one. So the result, so yeah, all you really need to calculate the gradients is calculate the errors the same way that we did before for the cost function. You multiply those errors times the inputs, and those give you the gradients. And the gradients are going to be, negative if you need to move, increase. So we'll have one gradient for each one of the dimensions that we have in our data here. Right? So if we're using just one feature, X will have two columns. We'll have a dummy intercept feature and one for the size in square feet. So we'll end up with two gradients here, one for the slope and one for the intercept. And if they're negative, that means we need to add to that theta to go in the right direction. If they're positive, we need to subtract from it. Right? So yeah, that was the gradients for some particular input that we started with for a random starting theta here. And given the gradients, gradient descent is just you keep iterating. So you start with a random theta, so often we just start at 0. So all the parameters just start at 0 to do gradient descent. You calculate the cost, you calculate the gradients, and then the next step, so that you update theta based on those gradients. So and the eta here is the step size. Right? So if you make that bigger, you're going to be taking bigger steps, and if you make that smaller, close to 0, you take really small steps. But again, the gradients will be negative if I need to go in the positive direction. So let's say eta is 1. So if I have a negative gradient, you'll actually add to theta. Right? You'll have 1 for each of your dimensions here. Right? So if I have 2 parameters in theta, my gradients are going to have 2 parameters, 1 with respect to each one of the features that we're trying to minimize here. And if it's negative, we'll actually go in the positive direction. And if the gradient is positive, we'll subtract from theta. So that goes in the right way, but we just do that based on this. So this is what a meta parameter. If your eta is too small, it might take more than, we're just hard coding 1,000 or 100 iterations here or whatever. I can't remember. Probably pass that in as a parameter 1,000 times here. But yeah, if your eta is too small, it might take more than 1,000. If it's too big, though, you might diverge. You might be going away instead of going down towards the gradient, towards the global minimum. So yeah, the most real implementations of gradient descent, instead of doing a fixed number of iterations, they will check how the cost is changing. And if the cost stops changing, that means that you're close to the minimum. So once from one iteration to the next, if the cost hasn't changed very much within some threshold, you'll go ahead and stop. If it's changing too much, you'll detect that you're diverging. So so you might see there's things called solvers in scikit-learn, like the atom solver and things like that. Those are really optimization methods. So a lot of them will use some sort of dynamic. They will change this parameter. So you might start off big in order to get into the general area, and then once you detect that you're in the general area, you start decreasing that so that you make certain you don't diverge. That's kind of really what the atom solver and some other more sophisticated optimization methods that are used in scikit-learn and other areas for machine learning are doing for this. Okay. So I did want to just, if I can, I want to, remind people about the assignment 3. I'm just going to bring that up. We got, 5 more minutes here. See if anybody has any questions on that. And so we'll get in. I guess we're going to have to wait till next week to get into some of the actual real heart of some of the stuff you need to do for assignment 3. But let me just mention a few things here in the last few minutes. So let me open up my assignment 3. Well, that's opening up. I'll remind again, so also don't forget about the class project stuff. So I did mention that at the top of the session today, but I am looking for people to accept the assignment and put in a bit of a description of what they're going to do and indicate which data set they're going to use. I'm going to try and look at those today for anybody that's done that to make certain I don't have any duplicates. Requests for the data set to use. I'll try to look at that today and tomorrow and Friday, but you should get that done by Friday. Let me know if anybody has a question about that or has a data set they're not certain I would allow to use or a question about that. So, yeah.
The project description.
Mm-hmm.
Can you please explain what it
I mean, yeah, it's a little bit, in general, the project's a little bit open, and so I am asking to, the data set you select, at least get an idea of it, so at least look at, what features it has, what columns it has, describe those a little bit, so, I won't hold you to this, but you ought to say, well, it's describe it, it has these many samples. These are the features that look important, and this column is going to be my label column. I think I'm going to be doing a regression, or I'm going to do a classification on that label data, that kind of stuff. Maybe make some guesses, but from the description of these features, I think these might be important ones. So I want to look at those, something like that. So I'm hoping people will at least convince me that they kind of looked at the data and kind of had a feeling for what was there and what they might need to do to work with it. All right, and we do have our assignment 3 is due next week. We'll go into more details of this next week. For one thing, I noticed I forgot to set the due date on that, or reset the due date. So if you could change that, but yeah, that should be Friday the 21st is when I'm looking for the assignment 3 here. So we're going to be doing a polynomial regression. So we're going to be doing a nonlinear regression in this assignment here. I haven't talked about that yet, but the whole thing of assignment 3 is we've got a set of data that is really nonlinear. So a line isn't a good model. We need like a quadratic, or actually you need a higher. So you might need some terms in there with to the 4th or 5th power or something like that for this set of data here. Yeah, so all this stuff, the majority of this is in the next week's notebook, where we begin talking about what it means to fit a model, what an underfit model is, or overfitting a model to the data. So those are the first kind of steps that you have to do. Get the data loaded, but then try and create a model that's underfitting it, and then one that's definitely overfitting it. And then from those information, that gives you some information about the data that you're trying to fit if you're doing a regression problem like we're doing for this assignment 3 here. So from there, then we ask you to use some regularization in order to try and get a better model. Okay, so yeah, all this stuff I'm realizing I haven't really talked about, but this is all in the unit for next week. So I mean, we are doing regression problems, so all the stuff that we talked about today applies. It's just that our data that we're trying to fit is going to be nonlinear in this case. So we have to add on to the stuff that we talked about today and on Tuesday in order to be able to successfully do gradient descent, but try and fit a nonlinear function instead of a linear function. That's really what polynomial regression is about from our next chapter in the textbook. It's in this the next section in the textbook that we'll be looking at next week here. So, okay, yeah. So yeah, there's a lot of stuff, but you should definitely get started on it. Start looking at it, and we will. Get into the details of this next week. So yeah, if you haven't looked at the notebooks next week, starting with polynomial regression, so all the stuff is discussed, polynomial regression, learning curves, and things like that. So yeah, our goal next week we'll start by looking at those notebooks as well as talking specifically about what you'll be needing to do for the third assignment. Okay, so that's all I kind of wanted to go over for today. So. All right, any last questions or anything? That stuff?
Project?
Yeah, project.
So I would like to use a data set that is not available from public. It's a personal data set.
Okay.
So I want to
Sure, sure. Yeah, I mean, in general, I mean, it's not only okay, it's I encourage that if you have a personal data set, but yeah, you might want to check with, well, probably the best thing to do, maybe shoot me an email so I can look at it specifically, but yeah, you will need to, it will have to be something that you can share. So you'll have to have something so that I can actually see the raw data, and you probably should try and get that set up by Friday. So, I mean, if it's small enough to fit in a separated value file or some plain text file, just do that, put it up there in your data subdirectory. If it's a little bit bigger than that, you might have to write some sort of a script in order to get it from somewhere or something like that. So, but that would be ideal. So if it's no more than like a megabyte or two, you can just go ahead and stick it into your GitHub repository and put it in your data directory in whatever format you have. But yeah, if it's not a publicly available one, you might want to spend a little bit of time on writing up the kind of the descriptions and stuff a little bit more, so that give me an idea of what's in there and how you got it, maybe. And
Is there a requirement for minimum samples in there?
well, yeah. I mean, the general thing for anybody that might be watching this is, I don't really want people to use just completely trivial ones. So you shouldn't be using like those most popular ones on the UCI data set. But yeah, I mean, as a rule of thumb, I mean, if it's only like 100 or a couple hundred samples, I might question it. Yeah, so I mean, it ought to have a couple of thousand samples at least or something, so that it's interesting to do something with for this class. Yeah, that's something to keep in mind. Yeah. All right. Yep. So that's it. I'll see you guys next week then. Check this recording here. Let's go ahead and